Yeah, so am I audible to everyone? Yeah. Okay. So this is the last part of the body plot. Afterwards, we are going to study transient response, not the AC response or the frequency response. So the thing which we have studied just now, it's an AC response or AC analysis or the frequency response, right? Where x-axis is frequency and y-axis is generally magnitude. We measure generally the magnitude in decibel. Just for a quick summary, can you tell me what is 66 dB in volt per volt? Sorry? Oh, you are IITian. Quick, quick. Huh? Why 10 to power 6? It's equal to 2000 volt per volt. Okay, let's try one more. 72. 72. Huh? 4000. Okay. So you can like look at these numbers. These numbers are very important. Anyway, so let's assume that there is a system which is having the second order. Second order is a system where the denominator, the maximum power is actually the number is 2. And there are few more quantities I am going to introduce. These are very commonly used everywhere. If you are learning even communication, if you are learning control or anything you are learning, most of the time the system is second order because this is the reality, right? So if the system is second order, okay, and which looks like this one, which will have some of the terms like omega n, you are going to call that one as natural frequency. Zeta is damping ratio. Right? Other things are known to you. Other one is the Laplace operator. Right? So now I'm asking you few things as you already expert on Bode plot. I'm drawing the magnitude response and I'm asking you okay, so can you tell me the order of this system? 2. Okay, how did you find out it's 2? Number of poles are 2, right? Can you tell me the system is stable or unstable? Or let's talk it in a different way. This how much phase contributed by the system? How much phase, effective phase, contributed by the system? Okay. How much phase contributed by the system at UGBW? That might be better word. The phase. Hmm. Yeah, you are right. You're saying something. Yeah. Yeah, it will be minus 90, not plus. It will be minus 90. The reason is every pole is going to contribute from 0 to minus 90 degree. So at 0 frequency, you are going to have the phase of 0 degree. At infinity, it's minus 90. And exactly at the pole frequency, it will be minus 45 degree. Right? So phase margin is equal to 90 degree plus 90 degree. Right? So maybe in future, there are many places where you are going to say that whether the system is stable or not, there are various condition which you are checking. Yes, Swarna. So, what are the condition to find out the system is stable or not? Yeah. Yeah, so you are saying something? Not less number of poles, but all the poles location has to be left hand side of the S plane, right? This is the first condition. But by looking at this, you cannot say that the system is always stable. Stability is measured from phase margin. If it is more than 45 degree, or let's keep it exactly equal to 45 degree, then there will be some ringing. If it is 60 degree, one ring, or when I'm saying ring, it's about, if this is input, the output look like this one. So in 60 degree, this is V in versus V out with respect to time, right? So this is what we are looking for. So this system which we have drawn just now, what is the phase margin of this system? It's 90 degree, right? So the system is stable. But what if we are going to keep exactly on top of UGW, I'm keeping my second pole minus 40 dB per decade. So can you comment on phase margin? Can you tell me what will be the phase margin? Yeah. Somebody told some number. Hmm? Yeah, so the phase will be exactly minus 135 phase, not phase margin. Phase margin has to be added 180 degree more. So your phase margin is equal to 45 degree. So in this case, you are going to see some ringing for sure. There is no other way. But as you are keeping this pole other side, means outside UGBW, the system will be having phase margin greater than 45 degree. If it is lower than that, you can see some of the ringing. If it is going inside, you will see something like a phase margin of minus 90 degree also. Sorry, 0 degree, right? If it is here, let's assume that second pole is here. So how much phase margin will be there? Phase margin is 0 degree, so you will have some ringing, right? So you cannot avoid it. All these systems are unstable. If the system is just first order, means it's the best system which you can have, but you cannot avoid extra poles and zeros. You cannot avoid extra poles and zeros, just for your understanding. Yeah, it can be negative. If it is, as it is negative, it's worst system, means the output will be like this, right? You will not see anything stable. Hmm. Phase, okay. So Komal, when there is a pole like this, okay, can you write down the phase equation for the same? Let's keep it 1. Minus tan inverse omega by omega p1. So if I am looking at the frequency which is 0 radian per second, then what will be the phase? How much? 0 degree. If you are at infinity, what is the phase? And what is the phase when you are exactly at omega p1? I'm looking for your answer, Komal. Yeah, minus 45, right? Now let's assume that there is another pole, omega p2. So effectively, I'm going to write another equation which will have this one. So it's not only because of one pole, but it's because of two poles. So you have to write down the equation from 0 to infinity, and at 0, the phase is 0. At infinity, phase is minus 180 degree, right? At omega p1, if omega p1 is less than omega p2, omega p1, how much phase will be there? minus 45 degree, right? At omega equal to omega p2, how much? Minus 135. So now you have to look at the location of pole, and you are going to measure the phase margin at frequency of UGBW or gain crossover frequency. Right? When you are doing this, you can substitute that thing here at omega equal to gain crossover frequency, and you can find out the exact number. Right? Through your calculator, you can do this. Right? I'm avoiding this because this is part of control theory. Right? Those who are studying control and those who are going to study Bode plot, that's the way they are learning. But these are the like information we wanted as circuit designer. Right? So, are you confident enough for this? Right? Yeah, because okay, okay, everybody understands digital system, right? This is very easy thing. I'm talking about this because Rohit came to one digital uh, seminar. So, do you understand fan out and fan in? Fan out and fan in, because that is what he was talking about, and you were saying yes. I understand you didn't understand. That's why I'm talking about this. Okay. Is there anybody who understands fan in and fan out? Fan in and fan out. Okay. हाँ, AC भी लगा सकते हैं. So, what do you think? Yes, Vaishali, Swarna, and Komal. Yeah. What do you think? Yeah. So ask me. Huh? Previous. Okay. So okay. Second term. Look. Mhm. You tell me. So omega p1 is much lower than omega p2, right? That is, I wrote it here. If you look at it here, right? Otherwise, this will not happen. And that is what I was keeping all this assumption. If they are close, then you have to calculate. There is no other way, right? Right. So then maybe MATLAB will work better than me, right? Yeah. Any doubt? Okay. So let's go to the thing which I was talking about, fan in and fan out, right? Okay. Like answering two questions, one by Rohit and one by Divanshu. So fan in and fan out. Okay. Is there anybody who understands fan in and fan out? Okay. Uh, we understand loading effect, Gaurav? Yes or no? We talked about just loading effect last lecture. Do you remember op-amp? We kept it in unity gain feedback, in negative unity gain feedback. And even somebody told me that it's a buffer, right? Right. So if the system cannot drive the available load, so generally, if it cannot drive the low resistive load, then you need some buffer, right? Similarly, in digital, we don't call it loading effect, but we are calling something called fan in and fan out. So fan out means how many number of gates, or what I can connect it after this logic gate. Whether I can connect another gate like this or not. Because every system, when you are looking inside, there will be some capacitance and resistance that will form some RC value, and that you need to drive. This inverter may not drive that one, means it's not capable of that. So accordingly, you are calling it fan out. Similarly, whether this inverter can connected after some of the gates like this, something like, let's, is it possible or not? That is also fan in, because it's at input side, this is at output side. So this is the easiest definition to find out whether they can drive it or not, right? Okay. So this is fan in and fan out. That is what he was talking about, right? Now the next question is, I'm interested in making a system.
If you give some signal in that input, obviously you get always an output. So what is actually meaning by the drive?
Okay. So when I'm talking about drive, if I'm giving this 1 and 0, right? So the output is 1 and 0, right? But this 1 is equal to the positive V supply, rather than calling it plus V supply, and minus V supply, right? This is equal to 1 and this is equal to 0. So when you are doing this experiment, you will understand, if you are having the bigger load, the output, if this is, let's assume that this is 1 volt, instead of 1 volt you are seeing something like this. This is called loading in practical. If the capacitor is very big here, very big capacitor, it's not able to drive it, right? This is one way. I'm talking about just an amplitude. But similarly, every path has some resistance, right? So let's call it path resistance, and this is the load capacitor. It might be coming from the next logic gate, which is deciding the fan out, right? When you are doing this, what output you are going to get, Divanshu? If this is input, which is connected here, this one, the output at this node will be like this. Do you agree with me? Right? This is happening because of one reason. This system is always stable. There is no ringing. Can you tell me the justification for that? Why there is no ringing? There is only one pole. There is only one pole. And the location of pole is known to you, 1 by 2 pi RC. Right? This system is going to give you phase margin of 90 degree, phase of minus 90 degree, and that's why there is no ringing. That's why there is no ringing. But if the dynamics of that logic gate is changed and it's not like this, there might be the case that there is an inductor, then this will not be the situation. The situation will change and the system will become second order. Do you agree with me? And that is what I am going to discuss now. So can you tell me where the pole locations are of this system? This very famous thing, right? You have done it in your school. Hmm? No, no, somewhere. So you have to write down the transfer function. So V out divided by V in is equal to 1 by SC divided by LS plus 1 by SC is equal to 1 by S square LC plus 1. Now somebody can help me in finding out the pole locations. Aishwarya and other people. Yeah. This is what you must have learned in school, no? Okay, so tell me. This has to be on your fingertip. If you like I, you can write down I, but we write down J. Right? So hmm, root LC, right? Okay. If it is in hertz, then you need to add 2 pi, right? So this is omega P1 and P2, two poles, but these are complex and conjugate, right? So then what is going to happen? That is what I wanted to discuss, because the system is second order and having some more terms which I am making the generalized way, because this will not be the reality. Where is it? Yeah. So this equation looks good on paper. In reality, this is not going to happen. There is something else going to happen, which is called Have you heard about ESR? Series resistance of inductor. So in reality, inductor is not a purely inductive. It will have some resistance, right? Then even for capacitor also same thing. And when you are going to add these resistances, your transfer function will not look like 1 by, it will be something else. That something else will be like this. It will have some more things, and you will see some of the surprising results. That is what I want to share. So what those surprising results are. So is there any problem? You can write down in your notebook. This is the only thing which we are going to study today. There is no other thing. Right? Okay. So now we know that the poles are available at two positions. One is minus zeta omega n plus or minus omega n square root of zeta square minus 1. Right? Yes or no? Is there anybody who does not know how to solve this quadratic equation? Right? It's minus b plus or minus 4ac and whatever, right? Whatever we used to do. That is what we have done it here, and we got this result. So we know the situation when zeta is greater than 1. We know that, because in that case you are not going to see anything complex and conjugate, right? Everything will be like s square plus 3s plus 2. You know that there are two poles, s equal to minus 2, s equal to minus 1. It's a second order, but the only thing is there are two poles which are at different places. Here they are at complex and conjugate when zeta is less than 1. Till that time there is no problem. Problem occurs when zeta is less than 1. Now, one more time, zeta is the one which we are going to call it as damping factor. We are calling damping factor because of one reason. When zeta is less than 1, you are going to see these fluctuations. I forgot to answer what Divanshu has asked. So, let's assume that this system is the one which is second order, and second order system is going to give you fluctuations. So if I am giving input like this, if the system is first order, no problem. As I'm telling you that the system is second order, it will look like this. But if you do not do this one, but you are doing something else, like if I am working at 100 megahertz, the clock which I have used right now, it's 100 megahertz. But if I am using same thing for 1 nanosecond, so just assume that this is 1 nanosecond, and output will look like this is happening because of one reason, that it's not settled yet, and before it gets settled, I'm switching to 1 to 0 and 0 to 1. So such system is not good system for any digital operation. Do you agree with me, Divanshu? So that is why we need good phase margin. Phase margin is going to give you guarantee that there is nothing like ring, and it's settled always. Or you have to make sure that the time constant is less than what you are operating on. Let's say you are operating on 1 nanosecond. The time constant of this circuit has to be less than 1 nanosecond. When I'm saying time constant, it's associated with the first number pole. Other poles are outside UGBW. Are you following me? Yeah. Right? That is why we are doing all these things. Right? Time constant because, do you remember this? Right? When I'm saying time constant, now time constant is not time constant, but it's equivalent to the first number pole. Right? So let's say tau 1s, tau 2s, and so on. So this is first pole, this is second pole. So first pole has to be less than, like 1 gigahertz, right? One reciprocal of 1 nanosecond will give me 1 giga. So it has to be less than 1 giga. Otherwise, the output will look like this one, right? It's not able to reach the amplitude if this is the thing. And that is what we are saying, that the bandwidth of my system is not good. That's why my output is not the correct one, right? Now are you following? Okay. So maybe a digital course, if you are studying somewhere digital system design, they should talk about this thing, right? Or if your professor is not talking about it, then you should ask this. He will answer it for sure, right? Okay. So we were talking about that second order system, which has two poles available at minus zeta omega n plus or minus omega n square root of zeta square minus 1, and zeta has to be less than 1 to get the complex and conjugate pairs. If it's greater than 1, there is no problem. Okay. Now I'm writing that h of s in terms of h of j omega, because I'm interested in magnitude response. So magnitude response says that it's equal to omega n square by this equation, because in numerator we had this thing. So when we are solving this, it's like this. If I am finding out the magnitude, it's square root of 1 by 2, which is in denominator. That's why it's going up minus 1 by 2, Aishwarya. Right? So this is what you are going to get. I'm interested in three things of my magnitude response. What is happening when omega is much lower than omega n? What is going to happen if omega is much higher than omega n? And what is going to happen when omega is exactly equal to omega n? These are three things we are interested in, right? By looking at this system, we know that the order of the system is 2, and before UGBW, Amol, before UGBW, we are going to see the slope of minus 40 dB per decade. Do you agree with me? Minus 40 dB per decade, because there are two poles. So there will be minus 40 dB per decade. And both the poles are available at the same place. They are not at different place. So this system is always unstable. It's going to give you ringing, right? So let's see what is happening. So I'm saying that if omega is much lower than omega n, this is equal to omega n square. What should I write here? If omega is much lower than, omega is much lower than omega n, means the multiplication of these two will be 0, right? Because one guy will be 0.01, one guy is 10, multiplication is smaller value, or you can say that we can neglect it and we can call it 0. So then, okay, minus 1 by 2, so you keep that, you should have 1, right? So 20 log 1 is equal to 0 dB, no problem. So when we are going to draw the magnitude plot, when omega is much lower than omega n, it's 0 dB. I should have drawn 0 dB. What is going to happen if omega n is much higher than omega n? What is going to happen? The answer is written. Can you find out in your notebook with all the approximations as an engineer, if you can do, right? Answer is already written. Right? So this will be again 0, first of all, because omega is becoming much higher and omega n is becoming much lower. So this multiplication will give you 0, right? So now in this case, it's minus omega square raised to omega, minus omega square raised to 2. So that will give me plus omega raised to 4 raised to minus 1 by 2. So then you have to check omega square and omega. So it will be omega n square divided by omega square. So you can approximate this to 1 by omega square, right? It's depending on this number, how much big this number is, so that you will have the smaller number, right? So it's depending on this. So if that is the case, it will be minus 20 log omega square, and effectively it's going to give you minus 40 dB per decade. So I'm not going into detail why it's minus 40 dB per decade. You know how to plot this one, right? So the next interesting thing is what is going to happen if omega is equal to omega n. I'm interested in the plot when omega is equal to omega n. What do you think? If omega is equal to omega n, what we are going to see, right? This is 0. Okay, 2 zeta times, let's make it 4 zeta square times omega n raised to 4, 1 by 2 is equal to omega n square times 2 omega minus 1 omega n raised to minus 2. This is gone, this is gone, so is equal to 2 by zeta, right? Everybody have, I made some, yeah, yeah, 1 by 2, right? 1 by 2 zeta, right? So now this thing is giving you some interesting result. That interesting result says that, but before going to that interesting result, I am asking you one more thing. You must have studied somewhere. There are two kinds of elements, passive and active. You know the difference between them, right? Passive does not need any power supply to make it on, or does not need any energy. Active can give you amplification, but passive will never give you amplification. You must have heard this somewhere. It will never give you amplification. You agree with me? So this is what you learn, and this is what known to us. Okay. Now let's look at the interesting result for the system which looks like this one. Right? So you are saying that omega n, when omega is equal to omega n, the magnitude is equal to 1 by 2 zeta. We already learned that if zeta is greater than 1, the situation is under control. No problem. Because there are two separate poles. I can handle them. But the situation when zeta is less than 1, this is what we want to look at here. So if zeta is less than 1, what is going to happen? If it is 0.1, let's say zeta is equal to 0.1, what are you expecting at omega n? 5. So you are saying that h of j omega is equal to 5, is equal to 5. So how much is 5? 14 dB. Very nice. It's in plus. Similarly, you can look at other plots which I copied from the document which I am following, and I gave it to you. So different, as you are increasing zeta, this shoot up is going on, right? And as I told you, this is nothing but this circuit, right? If it is LC, simple LC circuit, can you see something like at output, um, output voltage is higher than input voltage? Is it possible to have it? It is possible when there is some ESR is also there. So series resistance, resistance of capacitance, if you add all of these together, your system will exactly look like this one. Where zeta is the one, 1 by 2 zeta is the one. which is going to decide how much higher voltage you are going to look at the output, right? So once I remember, I created this experiment for IC161, and then people were getting more output than input. So they were saying there is some mistake in instrument, but there is no mistake in instrument. What you are saying is matching with this mathematics, right? So that was the interesting result you need to see. When you are going to maybe next time to laboratory, you can see that this omega n is generally some value which is which you need to find out in terms of LNC, or maybe you can add RLC, and that's why this is the most important analysis. One has to understand what is going to happen if I am going to add RLC together. This is the most important analysis you are going to learn everywhere. The reason is, when I am connecting DSO with function generator, I know that we all know about now parasitics, right? Parasitics resistance, parasitic capacitor, and parasitic inductor. So resistance will happen when there is a path. Every path will have some resistance. You cannot have like zero resistance path. There will be some, even milliohms will be there for sure, right? So there will be some path resistance. So you need to accommodate that path resistance for all frequency, no problem. If you work at high frequency where capacitor gets activated, and if you are seeing two plates, between those two plates there will be parasitic capacitors, right? Similarly for inductor, because some people are very mischievous and they are making such kind of connection, right? So if you are making this loop, right, you must have studied somewhere inductors will be created when such kind of things will be there. Then you need to understand all these equations which are difficult than capacitor. For understanding this, you must be studying electromagnetic theory, right now there is one course, Himanshu, there is one course. What course, name of the course which is electromagnetic theory? Gopi is teaching. Gopi Reddy. Huh? Electrodynamics. So in that course you must be studying this, how it's creating the inductor, right? So this parasitic inductor, and along with somewhere ground, all will be capacitor. This path will be resistance, right? So these things will happen. If you want, like one experiment we can do, like on a breadboard, there are many plates, right? Like vertical, horizontal. So you can choose any one of them, like this. Let's make this one ground, and let's connect this one using a wire. It's up to how much creative you are and how much this ring you want to make. Some people like it star connection, and there are many things they are doing. If you are connecting and if you are checking this parasitic, like I'm doing this with the wire, normal wire. Use normal wire and normal breadboard, because there are two plates and you have to work on frequency. DC it will not work, right? If you are doing with the frequency, you will observe the output at the midpoint, and it will exactly follow what we have studied just now, and you can find out all these things. This is just for your information, right? Not with normal inductor, right? You can make your own inductor which is parasitic, right? And you can make your plate capacitors, right? This is possible, and you can observe how much electrostatic charge you are giving, and how much parasitic effects are going to be contributed by such kind of setup. So this thing will be added in your electrical system, whatever you are making. If you are making such kind of system, still there will be some capacitor. You cannot avoid that, because it's coming from breadboard and there are many things. Just this is what I wanted to explain, and that is the reason why we are going to study RLC circuit, and that is the next part of the course, where we are going to talk about the RLC circuit and how it's working. Okay, This is say, damping factor, how it's increasing, and this is a table, right? I'm not going into it. If you want and if you don't understand, you can like let me know next time. I'll look at this thing and I'll give you the answer. Other than that, if the transfer function is reverse, you will see different answer. But before going to all these things, I would like to tell you very important thing. Now you are expert of order, you are expert of poles, you are expert of zeros. But this is what you can see from the transfer function. Just to check, let's can you tell me what is the order of this system? Okay, 4 now. Okay, okay. Now type of the system 1, right? We know all the pole location. When we will find out, those pole locations are known to you. Okay, so the interesting thing happens when it's not like this. Now I'm going to ask you, okay, so what is the order of the system? 1. What is the order of the system? How do you know this? You are answering because you have seen such system. Now I am doing it different way. Now tell me, what is the order of the system? You haven't seen this circuit, right? I also just made something which I thought. What do you think? Okay, how did you get this, by the way? Okay, let's keep something like this, or if you like, I can make something like this. Now tell me, this is more interesting, right? Looking By looking at transfer function, anybody can say that it's order and all these things, because that is the mathematician is doing what circuit designer or electrical engineer will do. What do you think? Any guess? Like, can you figure out? Yeah. So such questions are being asked in TI interview, right? Imanshu, right? So such questions are being asked. From the circuit, you need to tell the phase, delay, all these things. So somebody like some of the people have found out already. There is a trick that capacitor and inductor, these two elements are the one which are frequency dependent, right? And resistance is not. If there is something happening in frequency, there is some problem happening in frequency or something in time, you should blame only these two guys. There must be somewhere in capacitor and inductor which are creating a problem. If there is a resistance, they are going to contribute in terms of amplitude, right? It's not, they are not going to touch anything on frequency and time. Let's polish this question and let's look at this circuit. How many frequency dependent elements are there in this circuit? 1. Must, you have seen this circuit, so I just changing it. How many frequency dependent elements are there? 2. So as many number of frequency dependent parameter or elements you are seeing, effective number of frequency dependent thing, that is the order of your circuit. Effective, that's the new thing, right? Effective is not always work.
LC in parallel, is it one or two?
We'll find out. Right? So what do you think about this? Okay, you are talking about this. Effective means sometimes two capacitors are in series, some two capacitors are in parallel, inductors series parallel, so it's one. So that is what I was talking about. You are not going to treat them like two separate capacitor, two separate inductor, right? That is what effective means. So this is the thing, right? Order, and similarly those many number of poles for sure. Now the question is zero. Hmm. Okay, am I fast? Okay. Tell me.
Those should be different elements, or even if they are same, we can say order.
Same also. Effective number of capacitors and effective number of inductors has to be like some number n, right? You can check that. You can keep this circuit. You can make any circuit and you can find out what is the order of the system, right? So now, like, what do you think about this circuit? Is it low pass, high pass, band pass? Which kind of circuit? Yeah, Nakul. So at zero frequency, what is happening? By the way, so is it short circuit, open circuit? What is going to happen? Short circuit. Okay. When I was in BTech first year, so some of my senior used to teach us that capacitor blocks DC, but sometimes we used to forget. So there is a joke that if there is a DC which looks like this one, so it cannot go beyond this, so it's blocking. But if it is inductor, it can go from here, right? So at DC, capacitor will not allow anything to go, right? But inductor will allow; it can go from it. Right? So these are the jokes. So tell me, what is going to happen? DC, this will not allow, means it's open circuit, right? If it is open circuit, means V out is floating. Let's assume that it's zero. Initial condition is zero. What is happening at infinite frequency? This is short and this is open, right? So what you are going to see? This side or this side? What will be the answer? Yeah, Divya. Where is Manpreet? Manpreet. Okay, Manpreet. Yeah. So what kind of filter it is? Okay, high pass filter, right? Everybody agree with this one, high pass. And the system will be always unstable, by the way, because it's going to contribute minus 40 dB per decade, and the phase margin will be 0 degree, right? Exactly 0 degree, because two poles are at same location. So one pole is giving 0 to minus 90, two poles are going to give you 0 to minus 180, right? Maybe some more things we'll talk about maybe tomorrow, right? So this is ending of Bode plot. So there is no Bode plot. I was talking about transient response right now. So we are moving to next chapter. I'm going to teach it from a very famous book, Franklin Kuo. Okay. So this is I have one book which like this book is was written in maybe in 1941. Okay. So, huh? We are progressing in the course, so we'll learn that, right? We cannot learn in a single day. You stay with me till I should say analog course. I'll teach you everything.